It may not be necessary for understanding the fundamentals of quantum mechanics, but in order to do calculations, we really do have to change basis. So how do you change basis in occupation number notation? Well, we know how to do it for a single particle because we know that if we have one basis, then the basis vectors in that basis just have to be linear combinations of the other basis vectors. And we even know that these coefficients define a unitary transformation, and so we can immediately write down the inverse as the conjugate transpose. But how do we do that in occupation number notation? Well, in some senses it's very easy because we know exactly how to switch between the notation where we have the tensor product of a lot of these states for specific particles and our occupation number notation. We know how to do it, but we also know that it's quite complicated. We end up with these big symmetrized or anti-symmetrized states, and there's coefficients flying everywhere. And so we know that that's actually going to get really ugly. Now, fortunately, changing basis in occupation number notation, if we do it for the states, might be ugly, but if we do it for the operators, it turns out to be very simple. And we can demonstrate that fairly simply from here. This state here is a single particle in state Vk. So we can write that as if we were creating a particle in state K. So there's a creation operator that if we act onto the vacuum where there's no particles at all, we're going to get that state. Similarly, this state here can be created by a different kind of creation operator, one that creates a particle in that state. So if we apply a different kind of creation operator that creates a particle in uj to the vacuum, then we get that state. Now I want to revise what we've done here notationally. These things here are the vacuum, which is the same thing as saying that there are no particles. And so what we have is a set of 0 particles in every single state. And so I've written there just a set of zeros for all the possible states that a particle might be in. That could be infinite. So we're in occupation number notation there. Whereas up the top here, this is a single particle in a particular state. And similarly, this is a single particle. So these two lines are exactly the same objects in different notation. In the top line we have it in our original notation for single particles. Sometimes we call that first quantized notation, but try not to use that too much. And the next line we've got this occupation number notation where we've got occupation number operators and the occupation number states. Now down on this second line we could regroup the summation a little bit. We notice we have an operator acting on the vacuum there, and this thing here is just another operator also acting on the vacuum. Now it might be true that those operators acting on the vacuum give you the same answer. That doesn't necessarily mean that the operators are identical, but it turns out that in fact those operators are identical. It takes considerably more care to show that, but you actually know the exact definition of how things work in both notations, so you could show that yourself if you wish to. But the major point is you can always get the relationship right because you know how to translate that single particle state to the single particle state in the occupation number notation. And so if we know how a set of basis states transform for a single particle, then the creation operators that create those states transform in exactly the same way. And if we just take a Hermitian conjugate of both sides, we find that the annihilation operators transform in almost the same way. It's just got a complex conjugate. So if we know how to transform between any two bases, what happens when we transform to or from a basis with a continuous index? And the answer is, it works exactly the same way. So there we've gone into the position basis, and the annihilation operators are going to be... So this operator here annihilates a particle out of the single particle state Vk. And don't be fooled by the notation. This thing here is just an annihilation operator. It has a continuous index, but it's not a wave function. It's an annihilation operator and annihilates a particle at position x. Or another way of putting that, it annihilates a particle from the state x. And we can go backwards as well. And as usual, we move backwards and forwards between continuous and discrete indices. We move backwards and forwards between integrals and sums as appropriate. Also, the dimensions of the annihilation operator in the continuous case is different to the discrete case. Up here, we have here units of x. This we know has units of inverse square root x, and so this must have units of inverse square root x in order for it to have the same dimensionless units as the annihilation operator for the discrete index. People have a slightly frustrating tendency to call operators with continuous indices field operators. It's frustrating because it doesn't actually have any semantic content. This is simply an annihilation operator. There's nothing more to know about it than that. And finally, of course, you can go between two indices that are continuous, for example, position to momentum. In this case, of course, our coefficients have two continuous indices. So now we know that the easy way to change basis in occupation number notation is to transform the operators. And for this reason, we often work in the Heisenberg picture when we're dealing with calculations in this notation.